In this video, we're going to look at 7-71, 7-71, and we need to find the required diameter of bolt at B. And so, as usual, what we'll do is we'll make a free body diagram. Now, we're going to just need the lower beam. So we could probably just make a free body diagram of that lower beam. We have, say, A, and then there's, on the one I have, it's 3 kilonewtons. Over here, 2 meters. And then 2 more meters, it's going to be our force FC. And then we have, say, this force FB. And then, so we're going to have to, so let's say, sum the moments about A. And that'll be like minus 2 times 3 minus 4 FC plus, this is 1.5 plus, so this is going to be 4, 5.5. Equals 0. So notice we have 2 unknowns, so we're also going to have to make a free body diagram of the upper beam as well. So on that one, we're going to have FC. This is at 1.5. FB going the other way. Again, this is doing the upper beam. 1.5 meters. This is 1.5 kilonewtons. 5 meters here. 2 kilonewtons. 1.5 meters. And then we have, say, something at D, like this. And so once again, on this one, we'll sum the moments about D and set this equal to 0. So again, in my case, is minus 6 FC plus 4.5 FB plus, let's see what we're going to have here, like 3 times this 1.5. And then we're also going to have 2 times 1.5. And set that equal to 0. So we're going to have to solve these 2 equations simultaneously, this one and this one, because we have 2 equations and 2 unknowns. And so do that, solve equations 1 and 2 simultaneously. To find, that'll end up giving you, I guess, mostly you're really going to need FB. You could also find FC, of course, but you basically need FB. So then when you do that, find FB, then you can find the stress using this equation. So put your FB here, put your allowable stress here, whatever your allowable should go right here. Again, then put your FB over here. And solve for area. And solve for diameter from that. Now, the next thing we have to do is look at the bearing stress of the wood. And so you're basically going to have a, so let's say you have this washer here. And now you found the diameter. Basically, the diameter you found from the previous step would be this diameter here. Like the bolt is going to go through that. So whatever you find, there's going to be that diameter there. And then you're going to have an inside diameter, outside diameter. Here, let me call it OD for outside diameter. And so the bearing stress is going to be this this outer area here. Let's see, they're looking for bearing stress. Let me just double check what they have here. They assume that the whole is the same diameter of the bolt. The allowable stress for the bolt and the allowable bearing stress for the wood is going to be 2 pi. Oh yeah, so basically we're interested in finding this area right here. So the area of the washer is going to be equal to say pi over 4 times this outside diameter squared minus the inside diameter. This is what you found in the last step. Then, once again, go back to your equation, put your FB that you found here, and put the area of the washer here. And this, of course, will be the allowable bearing stress for the wood. So again, this you found previously. You found this in the last step. So the only unknown, and you're given this, so the only unknown is then find the OD. So again, just to review, we've had 2 simultaneous equations up here. We use those to find our FB. Then you can find the required area by putting the allowable stress of the bolt into this equation and solve for the area. Or like I said, you could put pi over 4 diameter squared here and then just solve for D directly. That's up to you. And over here, again, we want the bearing stress. That's kind of the stress that the stress on the face. And so for that, it's the same equation, except we need the area of the washer. Since it has a hole in it, we want the inside diameter, and that was the same as a bolt. So this is same as the bolt diameter. And then you're going to have some outside diameter. And that's what you're actually looking for, is this outside diameter. So the area of the washer is going to be pi over 4 outside diameter squared minus the inside diameter squared. And then solve for the OD by putting this into here. Put your allowable bearing stress here. And then solve for this outside diameter. The next one is 782. And we have this has this beam and has these wires. So, and then the beam is going to be displaced. So kind of show this down here. So it's displaced like this. And it's and this one right here, this is again the point C. This is the point B over here. Then there's some load P over here. And then there's going to be some reaction. This is going to be displaced. So this is FEC. FBD, like this. And so we're told that this has been displaced a certain amount. I don't know what we're going to call this. Maybe call this delta C. You call this maybe delta C or delta CE. And we're told that that has been displaced. Now on mine, the numbers I have, it's been displaced 10 millimeters. So we're going to have to find the displacement at B. Let me call that delta B. One thing nice about this, we can use similar triangles. Like, for example, we can say that this distance here, which is 357, divided by our delta C, which let me just put that down. That's going to be 10 millimeters. So this little triangle, let me actually maybe show it over here. So at B, we had this 3 meters. And we have like a delta B. And then we have the bigger triangle, which was, again, I'll just put the number down. There's 10 millimeters. This was 7 meters, like this. And so this is to this as that is to that. Then all you have to do is solve for delta B, and then find the strains. For this one here, that's simply going to be BD divided by delta B, divided by whatever length this is that you were given, LBD. So you found delta B up here, and use whatever length you were given for the total length of that wire. And that will give you the strain. And then same thing for EC. Once again, this is going to be the change in C, whatever you were given. Divided by the length of the wire, EC. Again, on yours, use whatever displacement you're given for the C and use whatever wire length you had for these two. And that'll give your strains. So we have a structure something like this, and we have a force P applied here. And we have some kind of angle, I'll call it theta here. Excuse me, let's not do that yet. We'll just first look at the original structure. So first of all, we're going to need the original length of AE. So original length of the part AE. And let me call that like L1. And of course, that's just simply going to be, so I think you're given this height here and this width on your diagram. So just simply take the square root of the sum of the squares, whatever this dimension is, and this dimension, that just Pythagorean's theorem. But now it's going to be moved a tiny bit. And this part is going to be displaced. Let me make another little picture down here. This is going to be displaced some amount theta. And then, so once that's displaced that amount, so it's going to be moved. So like this part is still going to be a little bit higher. And so now this part, let's say this was our original D up here. So this is going to be moved. So as this is kind of moved, that means this is going to kind of go down a little bit because this is going to be rigid. So that's going to stay the original H, whatever it was. So this is going to stay at 8. So if you had this over here and it's pushed, this is going to remain rigid. That length is not going to change. So it's still call that whatever you're given on that problem. That'll be your H. But then this side over here is going to be what, just H cos theta, whatever your theta you were given. Up here, this is going to be H sine theta over here. So when it's moved, when this part over here gets pushed a little bit, these are going to be like the new dimensions. You're going to have this one, and you're going to have this one here. But then, of course, E is still out here. This is E right here. Now, its dimensions are going to be changing slightly because originally, so now let's look at E now. Now what we're going to do, we're going to draw this whole triangle right here again. And we're not going to put this part in. We're just going to put this outside part in. And we determine, we've already calculated this. Let me put this over here. This side is going to be H cos theta again, whatever H was. And now this part over here, again, see, that's moved H sine theta. So this is going to be whatever your original width was. It's going to be H sine theta plus your original with W, because see, it's moved that amount. So now you pretty much have it. Now just take, let's see. Yeah. So basically, so then our L2 is going to be the square root of your H cos theta plus your H sine theta plus W squared, of course. That's going to be your new length right there. And then, so to find your change in L, it's going to be this new length minus your original length, like that. And then for your strain, is going to be your delta L divided by your original length. Remember, you always divide to find strain, you always divide by your original length. So again, let's take a look at this. To find the strain, we had to, of course, see how much change there was in the length. So we found out what the original length of this was. Remember, we're finding the original length of this. And it's just going to simply be using Pythagorean's theorem, square root of the sum of the squares of these sides. But now this is being pushed a certain amount, certain degree that whatever you were given in your problem. And then that's going to cause this top to move. Again, so we're assuming this H is rigid. So that's going to move from here to here, this slight amount, this small degrees, whatever yours was given, maybe 3 or something a little bit more, something a little bit less. So then after that's been moved, this top here would have gotten pushed 8 sine theta. The side would have kind of gone down. You know how something's here and it's going to kind of go downward, because when you push it, see, notice it was tall here. Then when you push it, it went down a little bit. So that's its new height. Is going to be H cos theta, whatever your theta was. And so again, then this point E here, we're just looking at the point E. I'm leaving out this part right now. I'm just looking at this total top here. So now you remember the original one, this original height was W, and it got pushed this extra amount. So we have 8 sine theta plus W is going to be the new distance between D and E. And then this side was H cos. And once again, take the square root of the sum of the squares to give your L2. So this is your new length. And so to find the change in the length, take your new length divided by your original length. That gives you change in L. Take your change in L divided by your original length, whatever you got up here, and that'll give you the strain.